So if I were to ask you, what is the first three terms of this binomial, x plus 2y to the power of 9, maybe you'd have no idea where to start, but hopefully you could at least think, well, if I can expand this thing out, then I could find it. So x plus 2y times x plus 2y times x plus 2y, and so on until you get to the last x plus 2y. And then you can see, well, we can FOIL this and distribute a bunch, and at that point you should realize this is tedious and ridiculous and no one wants to do this. The question is there a faster way? And the answer is yes. Enter the binomial theorem. The binomial theorem has some powerful applications to it. Sometimes they're more in-depth and more complex. It shows up in interesting places in mathematics. But for our use, we're just going to be studying how do we expand binomials without doing a lot of extra work. Binomial theorem here has these parts right here. Okay, so first off, we have the binomial, a plus b to the n power. Then we have these terms. Each one of these terms is the polynomial that results when we expand the a plus b to the n power. In the binomial terms, we have these portions here. These are called the binomial coefficients. And these portions are all designated. They can all be solved using this formula here. So if we can understand how to calculate that and then put, a to the n power, a to the n minus 1 times b, a squared b, that should be a to the n minus 2 times b squared, things like that. If we can figure out how to expand all that stuff, then we don't need to do the tedious, mind-numbing algebra of expansion by hand. So before we try that out in our original problem, let's look at actually finding the binomial coefficients on a couple test cases. So here we have this binomial coefficient. Now this isn't technically a binomial coefficient. It's actually called a combination, and we call this one specifically 7 choose 2. It's how many choices, how many groups of 2 out of 7 choices are there possible, and that's what this finds. And so we're just going to use the formula right here. 7 choose 2 is 7 factorial over 2 factorial times 7 minus 2 factorial, which of course 7 factorial over 2 factorial times 5 factorial. Now 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm going to simplify that by saying 7 factorial is the same as 7 times 6 times 5 factorial over 2 times 1 times 5 factorial. Because 7 factorial does continue on down to 1, I'm just simplifying how we write it. And I do that, as you can see, so that the 5 factorials cancel. And now we can see that the 2 cancels with a 2 and the 6, and we get 7 times 3 is 21. So 7 choose 2, that binomial coefficient would be 21. Okay, let's try another one. 11 choose 1. We can do the same process. 11 factorial over 1 factorial times 11 minus 1 factorial, which of course gives us 11 factorial over 1 factorial, which is just 1, times 10 factorial, like that. And now I'll do the same process. 11 factorial is the same thing as 11 times 10 factorial over 1, and then times 10 factorial. And those cancel, giving us 11 over 1, or 11. So 11 choose 1 is just 11. In fact, there are some special cases here. I could do any n choose 0, this will always equal 1, the same as n choose n. If we were to look at that, actually expand that, you would see we have n factorial over 0 factorial, which is defined to be 1, times n minus 0 factorial. But that's just n factorial over 0 factorial times n factorial. Those, of course, canceling, give us 1 on top, and 0 factorial, as I said, is defined to be 1, so we get 1 over 1, which is 1. The same thing happens when we do n choose n. We also get 1. Then if you do n choose 1, you always get n. The same thing is true when we do n choose n minus 1. We get n. Let's show the first one here. N choose 1. This equals n factorial over 1 factorial times n minus 1 factorial. N factorial is just n times n minus 1 factorial. 1 factorial is just 1, and we have n minus 1 factorial. Those cancel, and we just get n. So these are kind of special cases. Whenever we have n choose 0 or n choose n, we always get 1. Whenever we have n choose 1 or n choose n minus 1, we have n or whatever numbers on top there. Okay, let's use this idea and come back to our original problem. That is the first 3 terms of this binomial here. So let's go back and let's delete this expansion. We're not going to need that. So let's actually expand this thing out. First off, let's understand what our a, b, and n are. A equals x, b equals 2y, and n equals 9. Just looking at the relevant parts here. A and x, b and 2y, n and 9. Okay, using that information, let's expand the first 3 terms. We don't need to know the rest of it, just the first 3. The first term is n, I'll write it out like this, n choose 0 times a to the n. Well, n is 9. And a is x. Okay, that's the first term. The next term is n choose 1 times a to the n minus 1 times b. Again, n is 9, so I'm just going to add those in there. A is x, and b is 2y. The next, or the third term here, is n choose 2 times a to the n minus 2b. I messed that up down here. N minus 2. Now, again, n is 9. A is x. And b is 2y. And of course, we have the rest of the terms there, but we're not worried about those. So let's actually expand these 3 terms out. 9 choose 0. This is one of those special cases. 9 choose 0 is always going to be 1, because when you do the factorial, you'll see that it always cancels out to be 1. 9 choose 1 is going to be 9. It's always going to be whatever n is. And of course, 9 minus 1 is 8 times 2y. And then plus 9 choose 2. Let's actually expand that one out. 9 choose 2. 9 factorial over 2 factorial times 9 minus 2 factorial. We get 9 factorial over 2 factorial times 7 factorial. 9 times 8 times 7 factorial over 2 times 1 times 7 factorial. Those cancel. The 2 and the 8 cancel a little bit. Reduce to, that's going to be 4. And 9 times 4 is 36. So we get 36 times x to the 9 minus 2. Well, that's going to be x to the 7 times, oh, I forgot the square here, times 2y squared. 1 times x to the 9 is x to the 9. 9 times, right, there's this 9 times 2 here. We can combine those and get 18 x to the 8 y. I should actually write these things out. And then in this problem, we have 36 times whatever the portion of 2 is, but 2y is being squared, so it's going to be 2y times 2y, which is 4y squared. So we get 36 times x to the 7 times 4y squared plus the rest of the terms. And then x to the 9 plus 18xy, or sorry, x to the 8y plus 36 times 4, that's 72 times 2, so 144, x to the 7y squared. And then plus the rest of the terms, which doesn't matter because we're only looking for the first 3 terms, which these are the first 3 terms. So the binomial theorem, once you understand how to use it, you can find the first 3 terms of a long polynomial quite simply. If the polynomial is small, like, let me show you. If the polynomial was like x plus 1 squared, then it's much faster just to expand this thing out and FOIL it and, you know, find the terms there. But if the polynomial is long, like this one is, has the 9th power there, then it's going to be faster to use binomial theorem. Okay, here we've looked at finding the first 3 terms. We don't actually have to find a certain number of terms into the polynomial. We can actually find any term in the polynomial. For instance, let's look at x minus 1 to the 10th power. Let's ask the question, what is the fifth term? Okay, so we can look at the binomial theorem and look at the expansion. We know that n choose 0, a to the n is the first. N choose 1, a to the n minus 1, b is the second. N choose 2, a to the n minus 2b squared is the third term. N choose 3, a to the n minus 3, b3 is that's the fourth term. So the fifth term here is what we're looking for. N minus 4, b to the 4. This is the term we want. We don't really care about the rest on either side. We only want this term here. So we're looking for n choose 4 of a n minus 4, b to the 4th. This is the fifth term. And looking at our polynomial that was given, the binomial that was given, here a is going to equal x, b equals -1. That's how we have the a plus b, right? This is all equal to a plus b to the n. The b has to be positive, so for this to have a negative in here, the b must be negative, okay? All right, so b is -1 and then n is 10. Plugging in the relevant parts to our fifth term that we found. N is 10, so we have 10 choose 4. A is x, n is 10, minus 4, and b is -1 to the 4th power. Okay, 10 choose 4. That one's not really a simple one that we can see right off the bat. So we're going to have to actually expand that out and see what we get. 10 factorial over 4 factorial times 10 minus 4 factorial. We get 10 factorial over 4 factorial times 6 factorial. Now we get 10 times 9 times 8 times 7 times 6 factorial. 4 times 3 times 2 times 1 times 6 factorial. The 6's cancel. Get a little more room here. Also zoom in on this a little bit. The 6 factorials cancel, and now we can start canceling kind of portions here. 4 times 2 is 8, and 3 reduces the 9 to 3. So we actually have 10 times 3 times 7, which is 10 times 21, or 210. So our binomial coefficient for the 5th term is 210. Okay, let's actually add that into our problem here. Zoom in a little. So 10 to the 4th is 210. X to the power of 10 minus 4 is x to the power of 6. And negative 1 to the 4th power, that's just 1. So our 5th term is 210 times x to the 6th power. And so the binomial theorem can both be used to find like certain number of terms in a binomial expansion. You can find all of the numbers in a binomial expansion for sure. And it's also used to find a single term in a binomial expansion. Okay, let's talk about one last topic about the binomial theorem. Say I have this binomial and I want to expand it. This wouldn't be too hard to expand by hand. It would take a little bit, but it's doable. However, with this last kind of topic, it's actually pretty fast to do. First off, let's actually expand this to look at the terms themselves. The first term will be 4 choose 0 times x to the 4th power. The next term would be 4 choose 1 times x to the 3rd power times 2. The next term would be 4 choose 2 x to the squared power times 2 squared. 4 choose 3 x times 2 cubed. And the final term is 4 choose 4. There'd be no x in this case. The x to the 0, which is 1. And be 2 to the 4th power. So to actually find these terms, we need to find the binomial coefficients. And we can do that. This one's not terrible because these 4 choose 0 and 4 choose 4, those would both be 1. And then 4 choose 1 and 4 choose 3, those would both be 4. So really what we need to do is figure out what is 4 choose 2. 4 choose 2 is 4 factorial over 2 factorial times 4 minus 2 factorial, which would be 4 times 3 times 2 factorial over 2 factorial times 4 minus 2 is 2 factorial. That's why I did the 2 factorial on top. 2 factorial is just 2 times 1. And so that reduces with the 4 to make 6 in the very end. So 4 choose 2 is 6. All right, I'm going to continue this one down here. So 4 choose 0 is 1 x to the 4th plus 4 choose 1 is 4 x cubed squared times 2 plus 4 choose 2 we just found is 6 x squared times 2 squared. 4 choose 3 is 4 x times 2 squared or cubed. And 4 choose 4 is 1 times 2 to the 4th power. And of course, we can multiply the numbers together to get the final polynomial. 4 times 2 is 8. 2 squared is 4 times 6 is 24. 2 cubed is 8. 8 times 4 is 32. And finally, 2 to the 4th power is 16. Now, I want to take a moment here and look at these binomial coefficients. You see we have 1, 4, 6, 4, 1. Now, what I've done is I've created a little triangle here. It's called Pascal's triangle. And all I've done in this triangle is I have taken so we start with 1 at the very top here. And then we go down to the sides. We just put 1s on the sides. Then, putting a 1 here, we do 1 plus 1 is 2. We add them. And then, of course, we just put a 1 on the side. So again, we have a 1 here. We do 1 plus 2 is 3. 2 plus 1 is 3. And we have a 1 there. Starting with a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And we have a 1 there. And take a look at this line right here. 1, 4, 6, 4, 1. Well, that happens to be the same thing as our binomial coefficients in our binomial here that we expanded, 1, 4, 6, 4, 1. And if we start with n equal to 0, so we say n equals 0, this right here is the binomial coefficients for that. N equal 1, this is the binomial coefficients for that. Let me clean up the red just a little bit to show you a little bit easier to see. We have to start with n equal to 0. N equal to 2 goes to that. N equals 3 goes there. N equals 4, which is what we have, goes to 1, 4, 6, 4, 1, and so on and so forth. So it's an interesting combination between like a geometric kind of reasoning with the numbers. You know, this is a triangle that's shaped in a certain way, and the algebra that we have here. And that's not unusual. There's a lot of these connections in mathematics that you can make. And so I encourage you to always look for these types of patterns, and then think about, whenever you're using binomial theorem, think about Pascal's triangle. Pascal was a French mathematician in the 1600s, and he kind of found this triangle out, but he wasn't the first one. There's actually an ancient Chinese document from the 1300s, and it displays the same kind of triangle